Welcome to The Explainer. We hear all the time about these incredible AI models, but today we're going to pull back the curtain on the secret sauce, the one step that can truly make or break a machine learning project. It's called feature engineering. So, let's get right into it.
So a great question to start with is this. Why can't we just dump a bunch of raw data into an AI and let it, figure everything out? Isn't that the point? Well, it's not quite that simple. The truth is, real-world data is messy, it's inconsistent, and honestly, it's just not in a language that machines can naturally understand right out of the box.
Okay, check out this super simple example. Imagine we're looking at two things, a product's weight in grams and its price in dollars. Now to you and me, that's easy to understand, but a machine learning model, it just sees the numbers. It sees 1,000 and it sees 5. So without any help, the algorithm is going to think that the weight feature is literally 200 times more important than the price feature just because the number is bigger.
And that right there is the heart of the problem. Machines see magnitude, the size of the number, but they have no idea what it actually means. So for any algorithm that tries to figure out how similar things are by measuring the distance between them, like k nearest neighbors, these wild differences in scale can just completely throw it off and lead to some seriously wrong conclusions.
This is where the magic really happens. The solution isn't always a fancier algorithm, it's actually about preparing the data more thoughtfully before you even start. It's a process that's part science for sure, but also a whole lot of art, and we call it feature engineering.
So what is it really? Well, at its core, feature engineering is all about transforming that raw, messy data into clean, informative features that give the model the best possible chance to learn. Think of it as the crucial translation step from the chaotic real world into the neat, orderly world that an algorithm can actually work with.
The best way I found to think about this is to imagine a data scientist as a chef. Seriously, you wouldn't just toss a whole onion, an unwashed potato, and, a bag of flour into a pot and expect a 5-star meal, would you? Of course not. You have to peel, you have to chop, you have to measure and prep your ingredients. And it's the exact same idea for a data scientist. They have to prep the data before it ever goes into the model.
So what's the very first thing any good chef does? They make sure all their ingredients are in the right proportions, right? Well, for a data scientist, that means getting all of the different features onto the same scale.
It's kind of like making a smoothie with apples and strawberries. You wouldn't throw in one giant apple and one tiny little strawberry and expect it to taste balanced. You'd use them in the right proportion to get the flavor you want. In machine learning, we've got to do the same thing with our features, so that one feature doesn't completely overpower all the others just because its numbers happen to be bigger.
Now, to get this balance just right, data scientists have two main techniques they turn to all the time. The first is called normalization, and the second is standardization. They both try to get your data onto a common scale, but they go about it in slightly different ways.
Okay, so let's break this down. Normalization, which is also called min-max scaling, basically just squishes all your data into a really tight fixed range, usually between 0 and 1. This works great, but it has a weakness. It can be really sensitive to outliers. One single extreme value can kind of mess up the whole scale for everything else. Now, standardization is different. Instead of just squishing things, it recenters the data so that the average is 0. This way, you're not looking at the raw value, you're looking at how far it is from the average. This makes it way more robust against those extreme outliers throwing off the whole recipe.
All right, so our ingredients are all properly scaled. The data chef's next job is to clean everything up. We got to deal with any messy bits and maybe even simplify the recipe to make sure the final result is as clear and tasty as possible.
The thing about real-world data is it's often got holes in it. It's incomplete. So just like a chef might cut a bruised part off an apple, a data scientist has to deal with missing values. Sometimes you can just get rid of that row or column if it's not that important. Other times, you can make a really smart guess to fill in the blank. We call this imputing a value by using the average or the most common value from that feature.
Now, what if our recipe has hundreds of ingredients? That could make the final dish really confusing, right? A total mess. That's where dimensionality reduction comes in. And I know, it's a fancy term, but it's for a really simple idea. Let's reduce the number of features or dimensions in our data without losing the important stuff.
And there are two main ways to pull this off. Feature selection is like looking at 20 spices and deciding, you know what, I only really need the salt, pepper, and garlic. You're just picking the most important features you already have. Feature extraction, on the other hand, is more like creating a brand new spice blend. You take several of your original spices and combine them to create a new, more powerful one that captures the essence of all of them.
So let's zoom in on a secret weapon for that second approach, feature extraction. This is a technique that's like a Michelin star trick in the data chef's kitchen.
And that technique is called Principal Component Analysis, or just PCA. If you spend any time at all in the world of data science, you are going to hear about PCA. It is an absolute workhorse for simplifying complicated data.
So what on earth does PCA actually do? Well, think about two features like a person's height and their shoe size. They're related, right? They're correlated. PCA is a really clever statistical method that can combine them into a single, brand new feature that you might just call body size. It mathematically finds the most important underlying patterns in your data and creates a smaller set of powerful new features. These are the principal components that capture most of the original information, but without any of the overlap.
And the benefits here are huge. When you use PCA, you can compress your data dramatically, which saves a ton of storage space. It makes your models train way faster because there's just less to compute. And, most importantly, it gets rid of those redundant features by packing their information into one powerful component. It's all about being more efficient and focused.
Okay, so we've scaled, we've cleaned, and we've simplified our data. We've gone from a messy pile of raw ingredients to this perfectly prepped set of features. But let's tie this all back to the big picture. Building better, smarter AI.
At the end of the day, it really comes down to this. These prep steps, they aren't just tiny little tweaks. They can literally be the difference between a model that barely works and one that's state-of-the-art.
Ultimately, feature engineering is the bridge. It's the essential, often invisible, craftsmanship that translates our messy human world into the clean, numerical language that algorithms need to actually learn from. Because you can have the most brilliant algorithm on the planet, but if you feed it garbage data, well, garbage in, garbage out. So, the next time you see a headline about some groundbreaking new AI, I hope you'll think past the complex algorithm for a second. I hope you'll wonder, who was the data chef? What was their recipe? Because so often, the real genius isn't just in the cooking, but in the artful preparation of the ingredients that made it all possible. Thanks for watching.